This friend of mine says we're going to set out a balloon car. It's going to travel a certain distance. We can measure the distance it goes and the time, and then we'll express its motion with equations. Can you help? I said, sure. Let's write down some information. Final velocity is 0. Go to the physics textbook, get some kinematic equations, choose the ones we want. First step is to find the initial velocity. Distance is average velocity times time, and the initial velocity is twice the average velocity. We'll see that again later. Next step will be to find the acceleration. You can use this equation to find the acceleration, and we're good to go. Whatever your distance and time measurements are, you can graph them. This car went 4.5 meters. This car took 5 seconds to do it. But then my friend said, oh, we got a problem. I said, what do you mean? It's a parabola. It's a line of constant slope. It's perfect. He said, yeah, the problem is we sent the balloon car to the right, and your graph has it going backwards. I get negative velocities. I'd prefer to do this. Okay, I said, let's try an exponential decay. A different type of equation, but still we are moving fast and slowing down over here, and then we are stopped over there. Or are we? We're not exactly ever stopped with the exponential decay, because look at that equation for speed. No matter how big a time you put in, the speed never exactly gets to 0. Next up, let's find A. A is just the total distance we traveled. Okay, next step, find B. And earlier, I said that we'll have the initial velocity equal 2 times the average velocity. Well, the initial velocity, that's what happens when t is equal to 0. And it's complicated here. Time is the time measured with the stopwatch. T is a variable in the speed equation. Anyway, t is equal to 0. E to the negative 0 is equal to 1. So initial velocity is equal to a times b. And we can solve for b. Once again, it starts with measuring distance and time. The distance is a. B is equal to 2 divided by the time, and then these equations work, no matter what your distance and time measurements are. Again, it's perfect. Only my friend calls me up and says, you know, that new equation, still not perfect. I said, why not? He said, look at 3 seconds. At the 3 seconds, the car's supposed to be stopped at 3 seconds. The speed graph shows that it's still moving pretty fast at 3 seconds. What are you doing? I said, that's the magic of an exponential decay. It never really gets to 0. He says, you got to get closer than that. All right, let's look at some numbers. Calculating initial velocity, calculating B, calculating the speed at time equals 3 seconds. Should be 0, it's not. And the problem gets more noticeable the faster the car goes. What can we do? We can look again at the equation. Initial velocity is a times b. That's at t equals 0. Speed is a times b. And then plugging in t equals 2 over b, the speed will be 13.5% of your initial speed. How about a final speed equal to 2% of your initial speed? Would that be good enough? We can do it. Clear the deck. Look at this. That's our equation for speed. That's our equation for the initial speed. That's 2% of our initial speed. This is what it should be at time equals t. Our challenge is to find a new expression for b by dividing and taking the natural logarithm. And there we go. B is equal to negative the natural log of whatever the percent is divided by the time. And there we go. That's what our graph looked like before with a 13.5% final speed. And we can make it smaller and smaller and smaller and smaller, and now everybody's happy. Except not really. Look at that initial velocity. The initial velocity is now twice what we said it was going to be earlier. And if you adjust the percentage down so your speed really is 0, then your initial velocity would be infinite. So you can model the balloon car in multiple different ways, just don't expect any of them to work. The constant acceleration model gives you equations which give you parabolas, which is a problem. Exponentials look promising. This one has a decent initial velocity, but a problematic final velocity. Final velocity is better there, but our initial velocity is now too high. All of which raises the question, what exactly do we want our model to do? To be conceptually clear, to fit the data better? What makes a model work?